Chapter 2, Section 5, the Intermediate Value Theorem and Polynomial Inequalities. This is the last section of Chapter 2. Here is the Intermediate Value Theorem. For any continuous function, f of x, and two values, a, which is less than b, if f of a and f of b have opposite signs, so one of them is positive, the other one is negative, then the function has at least one real zero in the interval a to b. Let me show you a picture. Maybe it'll help us understand what this is saying. Here's the graph of a polynomial function, and I'm going to identify just two random points on this curve. And I'm going to say this first point right here corresponds to this a value here on the x-axis, which means this point on the y-axis would be f of a. This point here, I'm going to say that it corresponds to a value on the x-axis, and I'm going to call it b, all right, which just means that it corresponds to the y value, or the function value, on the y-axis, known as f of b. Now the function says that if f of a and f of b have opposite signs, and that's true here, f of a is negative, f of b is positive, then the function has at least one zero in the interval from a to b, so basically between a and b. And you can hopefully see in the picture that that zero is right there. That's a zero. So, and it doesn't have to be just one. It could be, it says at least one, right? So basically what this theorem is basically saying, if f of a is negative and f of b is positive, or if they just have opposite signs, one of them is positive and the other one is negative, the only way to go from beneath the x-axis to above the x-axis, you're going to have to cross the x-axis at some point to get from one point to another on the curve. And when you cross the x-axis, that gives you a zero. So in the next example or two, the instructions will say prove that there exists a zero in a particular interval. So prove that this zero exists. All you have to show is that when you plug in this left endpoint into your function, you get, positive or negative, and then when you plug in this endpoint, you get the opposite sign. Okay, so if you can show that you're getting opposite signs when you're plugging in these endpoints here, then you have proven that there exists at least one zero, one real zero between those endpoints. All right, here we go. All right, here it is. This is a cubic function, and you have to prove that there is a zero for this function in this interval. So all you have to do is plug in the number 1 and then plug in the number 2 and show that those outputs, those function values, have opposite signs. All right, so here I go. I'm going to plug 1 in. The remainder, we know by the remainder theorem, will be the same thing as g of 1 and will be the same thing as g of 2. All right, so here we go. So this and this, these are the endpoints of the interval. All right, so bring down the 2. 1 times 2 is 2. 1 plus 2 is 3. 1 times 3 is 3. This is 0, 0, negative 6. All right, let's plug in 2 now. Drop the 2. 2 times 2 is 4. 1 plus 4 is 5. 5 times 2 is 10. Negative 3 plus 10 is 7. 7 times 2 is 14. And then the sum is 8. So we just showed that g of 1 is negative 6 and g of 2 is 8. These have opposite signs, right? These outputs are opposite signs. That proves there is at least one zero in that interval. All right, because these function values have opposite signs, the intermediate value theorem says that there exists at least one real zero in this given interval. Good job, everybody. All right, now we will transition to polynomial inequalities. I just changed this number here. This is 4 examples in 1. The book calls this examples 1 through 4. I know the previous example said example 1, but that was the first example when it comes to the intermediate value theorem. These are the first 4 examples when it comes to polynomial inequalities. Now, please notice that these polynomial inequalities are all identical. The only thing that changes is the inequality symbol. Okay, so the first thing I want you to notice is that whenever they say greater than 0, they're asking you for above the x-axis. Same thing here, above the x-axis. Because greater than 0 or greater than or equal to 0 means positive. Less than 0, less than or equal to 0, that means negative values. That means you're looking for when the graph is below the x-axis. All right, very good. So what we're going to do is we are going to graph this polynomial so then we can see when is the graph above and when is it below the x-axis. So let's get a picture going first. All right, now when we say we're going to sketch the graph so that we can answer these questions, all you really need are 2 things, the end behavior and the x-intercepts. So let's get both of those pieces of information now. For the end behavior, I'm going to take the leading term from each factor and multiply. So the end behavior I'm getting is 2x cubed. Because the degree is odd with a positive leading coefficient, I know that my end behavior will be up forever to the right, down forever to the left. As far as the x-intercepts are concerned, all I have to do is take each factor, set them equal to 0, and solve. Okay? Barely could fit that there. So for the first one, divide both sides by 2, and you get x is equal to 0. For this one, add 3 to the right side, and for the last one, subtract 4 from both sides. So these are your 3 x-intercepts. They're all points at which the graph will cross through the through these points. In other words, they're all multiplicity 1, okay? They are not bounce points. All right, so let me scroll up here and show this graph. Okay, my x-intercepts are 0, 3, and -4. Notice that I did not find the y-intercept because it's irrelevant in this context for polynomial inequalities. It's going up forever to the right, down forever to the left. They are all points at which the graph will cross through the x-axis, okay? All right, everybody, let's answer the first question. Let me scroll back up and remind you what the first question is. The first question is asking you, when is the graph above the x-axis? So let's look back at the picture. You scroll back up here, or scroll down here. When is it above the x-axis? I'm going to highlight that for us right now, okay? It's above the x-axis from -4 to 0, and then it's above the x-axis again from 3 and forever. So for part A, when is it up strictly greater than 0? When is it above the x-axis? From -4 to 0, union from 3, and then forever. Okay, there are parentheses on these endpoints here because the inequality was strict. Now let's answer the second inequality, which says, when is the graph above the x-axis? Wait a minute, that's the same question as this one. The only thing that's different is that now that this is a non-strict inequality, I should include the x-intercepts, which means just put brackets on the x-intercepts. Oh, Okay, so then all I need to do is write my final answer for part B with brackets on the x-intercepts. Be careful, always put a parenthesis on infinity. All right, now let's go to part C and D. Part C and D are asking you when is the graph below the x-axis. For part C, it's a strict inequality. I'll be using parentheses on the x-intercepts. On part D, it's a non-strict inequality, so I'll be putting brackets on the x-intercepts. All right, here we go. We're looking for when the graph is below the x-axis. All right, it is below the x-axis from negative infinity all the way to 4, and then it's below the x-axis between 0 and 3. So then it'll be from negative infinity to negative 4, parenthesis, union, from 0 to 3. Once again, there's parentheses on your endpoints here because for part C it was a strict inequality. For part D, though, it was a non-strict inequality, so I can put a bracket at every x-intercept. All right, awesome. All right, next example, 2x cubed plus 3x squared minus 23x greater than or equal to 12. The first thing I think we should do is get a 0 on the right side. So let's subtract 12 from both sides, okay? And that'll give us this inequality. 2x cubed plus 3x squared minus 23x minus 12 is greater than or equal to 0. Now, let's make sure we understand that this inequality here is asking you when is the graph of this polynomial above the x-axis. And because it's non-strict, we will be putting brackets on the x-intercepts, meaning that we are including those x-intercepts in your solution set. All right, in order to get the graph, we need two things. In order to get the answer for this polynomial inequality, all we need are two things: n behavior and x-intercepts. Now notice that the degree of this polynomial is 3, so it's odd, and the leading coefficient is positive. That means the n behavior will be up forever to the right, down forever on the left. As far as the x-intercepts are concerned, we're going to need the rational zeros theorem to give us a list of possible rational zeros. And in this case, they are... All right, so we have these. These are the possible rational zeros. Now, we're going to have to start using synthetic division and trying some of these out. Because Descartes' rule of signs will not really shorten my list here. You can try, but it will not shorten your list. I'll go ahead and skip that for now, okay? All right, so here we go. Let's try some of these possibilities using synthetic division and see which one works. Okay, everybody, I tried a lot of them and it wasn't working until I got to 3. 3 finally worked for me. All right, so 3 is an x-intercept. Now, don't forget that your original polynomial is degree 3. That means this is degree 2. Let me move this up for us. This is degree 2. So which means it's 2x squared plus 9x plus 4. If I set this equal to 0 and solve this quadratic, I'll find the last two x-intercepts. Okay? So let's see. Does it factor? I hope it does. So let's check. All right, it does. Like this. All right? Set each factor equal to 0 and solve. So when you do that, you get 2x plus 1 is 0, or x plus 4 is 0, which gives you x is negative 4, or x is negative 1/2. So we have all of our zeros. We have all of the x-intercepts. I'll write them down here. The first one we found using synthetic division is 3, 0, and then negative 1/2, 0, and then negative 4, 0. All of them have multiplicity 1. They all appeared only one time for the polynomial. So the graph will be going through these points. All right, let's sketch the graph now. All right, let me plot my x-intercepts. So they are negative 4, 0, positive 3, and negative 1/2. And let's not forget our end behavior is up forever on the right, down forever on the left. All of these are points at which the graph is crossing through. All right. Now let's go back to the question. Do you remember the very beginning? We said that they are asking us, where is it at? There it is. They're asking us, when is the graph above the x-axis? Above the x-axis. So let's focus all of our attention on the intervals over which the graph is positive. All right? So it'll be above the x-axis from negative 4 to negative 1/2, and then again from 3 to positive infinity. Now we should be putting brackets on our x-intercepts because the inequality symbol is strict. So there's our final answer. All right, here's our next polynomial inequality. The first thing I want you to notice is the symbol. That symbol there means when is the graph below the x-axis. I also want you to notice that there is already a 0 here on the right, which is good news. I also want you to notice that this polynomial is already factored, which is fantastic news. All right, we need end behavior and x-intercepts. Now, in order to get the end behavior, I'm going to have to take the leading term from each factor and multiply, okay? Now be careful, this x right here is being squared. That's why I wrote x squared, okay? So then this gives us negative 2x cubed. Because the degree is odd with a negative leading coefficient, I know the end behavior is up forever on the left and down forever on the right. Now, in order to find the x-intercepts, all I need to do is take each factor, each variable factor, and set it equal to 0 and solve. So one x-intercept is negative 2, the other one is 1. Now be careful here. This x-intercept has multiplicity 1, but this one has multiplicity 2 because the power on that factor was 2. So there was 2 copies of this. So remember, multiplicity 2 means it's going to be a bounce point. Okay, this is a bounce point. Okay, everybody, let's go to the graph. All right, here's the graph. I plotted my 2 x-intercepts. I have my end behavior, and I know that at positive 1, right, you have a bounce point. All right, very good. Now, don't forget that they're asking you when is it below the x-axis. So I'm going to highlight that for us right now. Below the x-axis would be from negative 2 to 1 and forever. Now, we have to be very careful here because this strict inequality says do not include the x-intercepts. So we cannot include negative 2 and we cannot include positive 1. So our final answer will be from negative 2 to positive 1. Put a parenthesis on 1 as so that we can exclude it, right? We cannot include it. And then say union, pick right back up at 1, and then go to positive infinity. So it's basically this piece, union, this piece. Okay, this will be the last example for this section. Alrighty, the first thing I suggest us to do is to move 4x over to the left so that there's a 0 on the right. Now when you do that, you get x to the fourth power plus 3x cubed minus 4x is greater than or equal to 0. A few things here. This symbol means that they're asking when is the graph above the x-axis, and we should include the x-intercepts, put brackets on the x-intercepts because this is non-strict. All right, everybody, what we need to do is get the end behavior and the x-intercepts. Now notice that the degree is even, so the end behavior will match, both up or both down. The leading coefficient is positive, so they're both going to be going up. So the end behavior is like this. Now, in order to find the x-intercepts, you and I will start by, let's see, if we can factor all of this, then we can find the zeros. So we can start factoring by factoring out an x. That would give us with x, leave us with x cubed plus 3x squared minus 4, right? I'm going to set this equal to 0. I'm solving the polynomial equation. If I solve the polynomial equation, I will find the zeros of the function or the x-intercepts of the graph. Okay. Now set this factor aside. So x is equal to 0. Don't lose that. Okay, so don't lose that. What we need to focus on right now, though, is working on this trinomial. Okay, let's see if you and I could factor this further. Okay, now let's use the rational zeros theorem on this polynomial here. Rational zeros theorem on this polynomial. Remember P over Q, it will give us plus or minus, basically the factors of 4. So 1, 2, oops, sorry. I already have a plus or minus symbol on the outside, so I don't need to be writing that over and over again. Plus or minus 1, 2, and 4. Those are 6 choices. All right, so let's try one of these using synthetic division and see if one of them is an x-intercept. All right, I'm going to try 1 first, okay, everybody? Notice your coefficients are 1, 3, and then I put a 0 for the first degree term that is missing. That's super easy to forget. Degree 3, degree 2, degree 1 is missing, so I put a 0, and then negative 4. All right, let's try this out. It worked, everybody. So 1 is a x-intercept. And now this, remember, this was degree 3, right, everybody? Degree 3. So that means this is degree 2. So what we're going to say is, now that this is degree 2, we can factor this, hopefully, right, to find the last 2 zeros. All right, here we go. 1x squared plus 4x plus 4 is equal to 0. Well, this is what's called a perfect square trinomial because it factors like this. X plus 2 times x plus 2. In other words, it factors as x plus 2 quantity squared is equal to 0. You call this a perfect square trinomial because it factors as the square of a binomial. So you can see that all you need to do is take one copy and set it equal to 0. So then the other x-intercept is negative 2, right? But here, be careful. This is multiplicity 2 because there were 2 copies, right? 2 copies. All right, let's collect all of our x-intercepts. So one of them is negative 2, and then let's see if I remember. Another one is positive 1, and then don't forget this one, x equal to 0. All right, everybody, these are your x-intercepts. I am now going to show you a quick sketch of the graph, okay? So this is 1, and this is negative 2. All right, so your x-intercepts are the origin -2, and +1. Your end behavior is up on both ends like this, okay? Now, be careful. This is a bounce point. -2 right here is a bounce point, so be careful. Bounce off of it, and then come through this and through there. Now, remember, the original question, let me scroll up here so that we can see it. It's way up here, the very beginning. We have to look at when the graph is above the x-axis, and we will be including the x-intercepts. And of course, in interval notation, that means you'll be putting brackets on your x-intercepts. All right, so when is it above the x-axis? It's above the x-axis from -infinity all the way to -2. I'm supposed to include that x-intercept, keep going all the way to 0, and then pick back up from 1 to +infinity. So then, the final answer in interval notation will be from -infinity. Now, don't stop right here. Don't write -2. So you include, keep going. There's no need to stop. Keep going, and then finally stop at 0. Okay? Put a bracket because the inequality was non-strict. Union, pick right back up at 1, and then go to the right forever. This is the final solution set. All right, everybody, this is the end of this lesson and the end of Chapter 2. You made it through Chapter 2. Congratulations. I hope this lesson was a lot of fun for you, as it was for me, and I'll catch you later in Chapter 3. All right, see ya.